Okay, so today in this video, we're going to continue our study of power series. Now we're going to focus on differentiation and integration of power series. So let's just take a moment and look at a few of the results that we've proven so far. The first one here is a result about uniformly convergent functions, right? So sequence of functions is uniformly convergent, and it tells us that the limit of the integrals is the integral of the limit. So this is one of our key results. This allows us to interchange limits under certain conditions. So if you look in the course catalog and you look at the description of this analysis course, one of the main things you're supposed to learn about is when can you interchange limits. In other words, when is it the case that if you have multiple consecutive limiting processes, you can interchange those processes and end up with the same result. So, another way to write this, looking at this, is to say that the limit of the integral of the fn's is the integral of the limit, right, of the fn's. Why is this interchanging limits? Well, obviously you see the limit sign here, but keep in mind, and we'll learn about this in a few weeks, taking the integral is taking a limit. So this sign means you're taking a limit. Remember the limit of Riemann sums, right? This means you're taking a limit and you're taking a limit here. And we're saying when can you interchange those limits? And this result tells us that when you have uniform convergence of continuous functions, you can interchange the limits. Now, the second theorem gives us a way to go from sequences of functions to series of functions. So it says consider a series of functions and suppose that each function is continuous. And suppose that your series converges uniformly on your domain. Then the limit function is continuous. Okay? So we had the result that said that the uniform limit of continuous functions is continuous. And this theorem is just explicitly saying that's true whether it's the uniform limit of a sequence of continuous functions or if it's a uniform limit of a series of continuous functions. And of course, this plays right into what we need for our study of power series because a power series is a special type of series of functions. Each of your GKs is a polynomial, right? And we know the polynomials are continuous because the product of continuous functions is continuous and the sum of continuous functions is continuous. Constant functions are continuous. Each polynomial is the sum, a finite sum of a product of continuous functions. Okay, so this next theorem here tells us that if you have a power series with a positive radius of convergence, then the power series converges uniformly on any compact subset of the domain. Right? Now remember, why do we care about this? Well, we care because if we know that our series is converging uniformly, that allows us to, for instance, interchange limits. It allows us to conclude certain analytical properties about that limit. Okay? And then the last result here says essentially that your series might not be uniformly convergent on its domain, but it will certainly converge to a continuous function. So even if it doesn't converge uniformly to the continuous function, it might converge pointwise, but that's okay. The pointwise limit will still be a continuous function. So, looking here, this converges pointwise, pointwise, yes. Uniform, maybe not. Right? So we looked at an example. The example that we looked at here, a power series doesn't have to converge uniformly to that continuous function. It could just converge pointwise. Okay, so we're going to use all these facts as we're studying differentiation and integration of power series in this video. So let's start off with the lemma. And the lemma basically says if you have a power series with a positive radius of convergence, so let me add in here, r needs to be bigger than 0, then these other power series also have a radius of convergence r. They have the same radius of convergence. So one note that I would like to point out is that we need r to be positive. Do you know why we need r to be positive? What's wrong with r being equal to 0? Well, I've written it right here. This is an analysis course. We're doing analysis. And we don't do analysis on functions that have singletons as their domain. It defeats the purpose of analysis. Analysis is trying to investigate when limits exist, right? That means you need to know when things are near each other. You need to have more in your domain than just a single point. You can't talk about a limit if you just have a single point. Or, I mean, you can, but that's it's not meaningful, right? You're not able to do approximations if you just have a single point in your domain. It's you're just not going to be able to do analysis. It's not interesting. So we're doing analysis. We can't integrate unless we can look at the limit from the left, the limit from the right, right? We can't take derivatives unless we're able to look at the limits. So we need r greater than 0. We need to know that our power series is defined on an interval, not just defined on a singleton, okay? And then the second question is down here. It's a thought question. How are these three power series related? So A is our beginning power series, B is our second power series, and C is a third power series. Why am I saying B and C are power series? Well, they're power series because this is now the coefficient, right? So the coefficient looks a little different, but you still have coefficient times a monomial. That's a power series, and the same thing here, right? So A, B, and C, we're saying will have the same radius of convergence when r is greater than 0. How are these power series related? Well, you might remember from calculus that B is going to be the derivative of A. So B is related to the derivative of A. And C is related to the integral of A. So this lemma is going to ultimately tell us if you have a power series, then the derivative is another power series with the same domain, right? And similarly for the integral. Okay, so let's go ahead and get started on our lemma. I took the liberty of writing the hypothesis and claim out in advance. The hypothesis is just we have a power series and it has a radius of convergence r is greater than 0. And the claim is that this power series has a radius of convergence, say, of r, and also this one. So let's go ahead and do a sketch of the proof. And the reason why I'm doing a sketch is because this is not that detailed. The justification is not that detailed. We basically need to go back to our definition, well, not our definition, we need to go back to the formula for the radius of convergence for a power series. So I will say, recall that R must be equal to 1 over lim sup of the nth root of the absolute value of a sub n, right? So that's our formula for R. We actually have a formula for R. So if we want to compute the radius of convergence of this series, for instance, we just need to compute the lim sup of the nth root of this coefficient, n times a sub n. So we'll just say, notice that the lim sup of the nth root of the absolute value of n, a sub n, well, it looks kind of similar to the denominator in our R, but let's just work with this a little bit. I'm going to rewrite this as, and this is all as n goes to infinity. Sorry, I didn't write that down. I need the nth root. I don't need the absolute values around n, so it's just n. And I can use my properties of exponentiation to split this up into nth root of the absolute value of a sub n. Okay. Now the key is to note that the limit as n goes to infinity of the nth root of n is going to be equal to, I can rewrite this as n to the 1 over n, right? And I can rewrite n to the 1 over n as e to the log of n to the 1 over n. So then I'll get e to the 1 over n times natural log of n. That's just going to be n goes to infinity, that's going to go to plus infinity. The denominator is going to go to plus infinity, but logs grow so much slower than polynomials that this ratio is actually going to end up approaching 0. And we can use L'Hopital's rule to see that that ratio goes to 0. So by L'Hopital's rule, ln n over n goes to 0 as n goes to infinity. So since exponential functions are continuous, e to the ln n over n is going to go to e to the 0 as n goes to infinity, but that's just equal to 1, right? So this was a long-winded way of saying that n to the 1 over n converges to 1 as n goes to infinity. So since n to the 1 over n goes to 1 as n goes to infinity, the lim sup of this product is going to be the same thing as just the lim sup of the nth root of the absolute value of n. So we can take that and say the radius of convergence for our series in a sub n x to the n minus 1 is 1 over lim sup nth root n a sub n is 1 over lim sup nth root, absolute value of a sub n, which is r. Now there's one tiny point that we need to discuss. And the tiny point is, if I take this and rewrite this, technically this is n starting at 1. So if I rewrite this series in order to be able to use my formula for radius of convergence, I should really rewrite this as, I'm going to re-index, so it should be n plus 1 times a sub n plus 1, x to the n. And then n will start at 0. So technically, my coefficient for the nth term would be this, right? So technically, I should be looking at one over lim sup nth root of n plus 1 times a sub n plus 1, right? And then the absolute value of that. But the way to get around this is to notice that this series here with the a n times a sub n, x to the n minus 1, and just the series n a sub n, x to the n, both have the same radius of convergence because the behavior of the coefficients doesn't change. The only difference is to get from this power series to this power series, you just multiply by x, right? And x in and of itself, so here's x, right? X is a power series, but it's a power series with a radius of convergence plus infinity. So when you multiply a power series by a polynomial or any other power series with a infinite radius of convergence, the resulting radius of convergence of that product is going to be the radius of convergence of the original function. Okay, so that's why it's okay really for us to use just n a sub n as opposed to n plus 1, a sub n plus 1. We'll get exactly these same computations. Okay, and then similarly, so we did the first one here, so let's do a sketch of the second one. Similarly, first let's note this is a sub n over n plus 1. So we'll just say here 4. The series with a sub n over n plus 1, x to the n. Step 1 would be, where's that n plus 1? Let me just, yeah, to the n plus 1. Note that these two power series have the same radius of convergence. And then step 2 would be to compute radius of convergence equal to 1 over lim sup. And now I need the nth root of the absolute value of a sub n over n plus 1. So it's going to be 1 over lim sup, n goes to infinity, nth root of absolute value of a sub n times the nth root of 1 over n plus 1. So if I know that this converges to some limit L, then the lim sup of this times this will be the same as L times the lim sup of just this. Okay, and that was back from our limit laws earlier in the semester. So let's compute limit as n goes to infinity of 1 over n plus 1 to the 1 over n. Hopefully it's equal to 1, right? So I'm just going to rewrite 1 over n plus 1 to the 1 over n as e to the natural log of 1 over n plus 1. Going to be times 1 over n. And I can write that as e to the minus natural log of n plus 1 over n. That'll go to 0. So all of this is going to go to e to the minus 0, which is 1, as n goes to infinity. Okay. So this will be the same as the radius of convergence for our original function. Or, yeah, our original power series. Wait, sorry. So this is the justification. This is the justification that this is equal to that, right? Because that limit is equal to 1. Okay, so we have this lemma under our belt, and the lemma essentially says that this power series and these two power series will have the same radius of convergence whenever r is greater than 0. So now, let's go ahead and see if we can make a connection between these three power series. So the first theorem that we have, this is our first result, it's going to involve integration, right? And we're saying, suppose you have a function, you have this power series, we're just calling it f of x, and it has a radius of convergence r greater than 0. Then the integral, and the antiderivative of f, is this series right here. And of course, this series is going to have this radius of convergence. So to prove this, we just need to show that this integral is equal to this series, because our lemma will tell us that this series has this radius of convergence. Okay? So for the proof, here's what we're going to do. I'll kind of run through it here. Fix a x that's less than 0, but we also want to make sure the x is in our domain, because we're going to integrate our power series from x to 0. So x needs to be somewhere less than 0, but also bigger than negative r, just so we can make sure that for each t in our domain of integration from x to 0, f of t really can be expressed as this power series. Okay? So we're going to integrate and use the fact that we had from before about the ability to interchange limits whenever we have uniform convergence of a sequence. And this is essentially going to give us our result. So let's go ahead and walk through this. Let me get a fresh page here. Okay. So we're starting off with our integral from x to 0 of f of t dt. Here's our sketch. So the integral from x to 0 of f of t dt is going to be equal to, first thing I'm going to do is just replace f of t with the power series here, Because if t is in between x and 0, then f of t is equal to this limit, right? So I have the integral of the sum a sub n t to the n 0 to infinity dt. Okay? So this is just by definition of f. Now, what I'm going to do is I'm going to rewrite this as a series of functions. I'm going to consider this as a series of functions that is uniformly convergent, right? How am I going to do that? Well, remember, a power series, a sequence. A power series is a sequence of partial sums. So I'm going to rewrite this as the integral from x to 0. Now, I need the limit as n goes to infinity. I need a sub k, t to the k. K is going to go from 0 to n, right? And then dt. Now, my theorem from before says fn going uniformly to f implies integral of fn goes to the integral of f, right? So the limit of the integrals is the integral of the limit. So I'm using that theorem that we proved for sequences on this sequence of partial sums. I'm going to say I'm going to interchange my limits, right? And I'm going to get the limit as n goes to infinity of the integral so this is, so let's go back and put our justification. So series is sequence of partial sums. That's the justification here. And now the justification for interchanging these limits is interchange limits is okay with uniform convergence. And how do we know that we have uniform convergence? We have uniform convergence because we proved that a power series will converge uniformly on compact subsets of its domain. And 0x is certainly a compact subset of its domain. It's like this is super heavy stuff that we're doing. Whoa. Okay, so heavy hitting theorems that we've used. And we could even say, how do we know that this is a compact subset? Well, it's compact because it is closed and bounded. Remember? So we're pulling together all these things we've been learning this semester. Okay, so now I'm going to use just simple properties of integration to say that the Integral of sums is the sum of the integrals, right? I don't need anything fancy in order to interchange these because this is a finite sum. You only need the heavy duty machinery when you're trying to interchange for an infinite sum because now you have limit and limit. Here we don't have limit and limit, we just have limit, limit, and finite sum. Okay, so this is just going to be the sum integral from x to 0. I can bring the a sub k's out, right? So if I write a sub k, t to the k dt, we know how integration works. That's a constant. It has nothing to do with t, so I can just bring that in, right? And then if I want to integrate it's not going to let me do this. Let me see. Okay. If I want to integrate t to the k, I can use the fundamental theorem of calculus to say that's going to be t to the k plus 1 over k plus 1. Evaluate t equals x, t equals 0, right? And I plug it in and I'll get 0 to the k plus 1 minus x to the k plus 1 all over k plus 1. Now I've got the sum a sub k. Okay. And of course, I don't really need the 0 to the k because k starts at 0. So that means we're looking at 0, 0 squared, 0 cubed, 0 to the 4th, blah, blah, blah. So I really can erase that. And I can bring this negative out front. And I can even bring it out front here, right? So what do I have? Ta-da! I have that series, that power series that we started with from before. Because limit n goes to infinity, 0 to n of these partial sums, that's just going to be equal to minus 0 to infinity a sub n plus 1, x to the n plus 1, right? And the last thing we would do to take care of the minus sign would be go back and say if we integrate from 0 to x, then we'll get minus the integral from x to 0. So the integral from 0 to x, f of t dt, is going to be the integral, right, minus the whatever we got originally. And this is going to be valid on that same domain. Okay? All right. So that is that theorem right there. This is a sketch here. The only thing that's missing is the final part right here. But I just want to go through and explain how do we get that this is equal to that? How do we get that this is equal to this, right? I wanted to justify each step because we're pulling in a lot of rich theory here. Okay, let's do this example here, and I think this is one of the exercises in Ross. We're supposed to express this function as a power series, and we're supposed to use the fact that each of the x is equal to x to the n over n factorial on r. So if I'm looking at this, if each of the x is equal to this power series, and this is valid for all x and r, that means that it's valid when x is positive and when x is negative. I can easily replace x with minus x. because of my domain, right? So minus x to the n is going to be equals 0 to infinity. So I'll have minus 1 to the n, x to the n, over n factorial. And then the other thing I can do is replace x with t squared. So I'll get that e to the negative t squared is going to be equal to the sum from 0 to infinity, negative 1 to the n, t squared quantity to the n over n factorial, and this will be valid whenever t is in R. So that's just going to be negative 1 to the n, t to the 2n over n factorial. Okay? And so now I'm going to do the term by term integration to compute the integral from 0 to x of this series. Okay? Let me copy this because I'm not going to remember it. So I'll say here, so f of x is the integral from 0 to x e to the minus t squared dt. And that's going to be the integral from 0 to x. Let me do the color. Change that to black. I need this to now be dt. I can do term by term integration, meaning I can interchange this limit with this limit. I can switch them out. So that's going to be, let me double check because I need to, yeah. Sometimes you need to check to see if your index changes. So if I'm integrating, then if I start off with 0, I'm also going to start off with 0 here. So it'll be from 0 to infinity, and I'll have the integral from 0 to x, negative 1 to the n, t to the 2n over n factorial dt. And again, these have nothing to do with t, so I can take them and move them out front to the front of my integral. So we'll have the sum, negative 1 to the n over n factorial. Now I need the integral 0 to x of t to the n, t to the 2n. So that's going to be t to the 2n plus 1 over 2n plus 1. I'm evaluating it at x and 0. When I do that, I'm just going to get x to the 2n plus 1. So this is my final answer, and this is going to be valid for all x and r. How do I know that it's valid for all x and r? Because for any x and r, I can use this to replace this, right? And I'll know that the convergence is uniform. So that will allow me to interchange my integral in my limit. Okay, so we're done with that one. And let's talk about this. This is our last main result here. This is on term by term differentiation. So again, suppose you start off with a power series with a positive radius of convergence. The claim is that f is differentiable, and this is its derivative. And of course, our lemma that we proved in the beginning of this video tells us that the radius of convergence for this derivative will be the same as the radius of convergence of the original function. So let's go ahead and get into this. And this proof has 3 steps. So the first step is to let's just name this Let's just call that g of x. So now our goal is to show that f prime of x is really equal to g of x, right? From the lemma, we know that g is a power series that converges on negative r to r. So we'll just put here by the lemma in today's video. Okay, second step is G is a power series, so it's going to converge uniformly on compact subsets of its domain. And that means that we can integrate term by term on compact subsets of its domain. So let's go ahead and integrate term by term, integrate G term by term, and let's see here. So G is n, a sub n, x to the n minus 1. So we need the integral 0 to x of n, a sub n, x to the n minus 1. And we're going to integrate that with t dt. So I believe this is the integral of g of t dt. So we're going to fix x in 0 to r, so that we're certainly dealing with a compact subset of our domain. Integrate term by term, and what am I going to get? Well, because my convergence is uniform, I can interchange these limits. So I'll have integral 0 to x n a sub n t to the n minus 1 dt. And again, n a sub n has nothing to do with my variable of integration. So I'm just going to move those out the way, move those in front. Okay, so now I need to figure out how to integrate t to the n minus 1. That's just going to be t to the n over n. And this is from 0 to x. So we'll get x to the n minus 0 to the n over n a sub n. And now I do need to be careful because if n is equal to 0, then 0 to the 0, sorry, well, wait, let's see. Do I need to be careful? No, I don't. I don't think I do. Because I wanted to double check. Okay, if n is equal to 1, then I've got 0 to the 1. So that'll be 0. And n is going to be 1 or bigger. So 0 to the n is always going to be equal to 0. Also notice that we have an n here and we have an n in our denominator. So I'm sorry. So notice we have an n in the numerator, n in the denominator. Those cancel out. I don't need to write that. I'll just be left with a sub n times x to the n, which is precisely f of x. Okay, so the argument for when x is less than 0 is very similar to what we did before. Right, you do it at the end, you're going to get minus, and then use the properties of integrals to rewrite it. Right, so step 3 is essentially to say that we have a function, right? Use a fundamental theorem of calculus to say that because we have a continuous function and its integral is our original function f, it must be, right, it's antiderivative. It must be that the derivative of f is equal to g. Okay. All right. So we'll conclude the video just by going through another key example. And we're basically going to manipulate the geometric series by integrating and differentiating to get different power series representations for other functions. So when I look at 1 over 1 minus x squared, the thing to note is that 1 over 1 minus x quantity squared is the derivative. Let's see here. If what happens if we take the derivative of 1 over 1 minus x? So that's 1 minus x to the minus 1. So if I take the derivative, I'll get minus 1 minus x to the minus 2 and then times negative 1. I'm doing the chain rule here. Oh, okay, yeah. So this is the derivative of 1 over 1 minus x. So if I have the power series for 1 over 1 minus x, that is x to the n. And this is valid when absolute value of x is less than 1. Then the derivative is going to be, let's go back here. We can do term by term differentiation. And I'll have n times a sub n x to the n minus 1. So the derivative of is going to be I'm interchanging those integrals. I'll have n x to the n minus 1. Okay? And this means that 1 over 1 minus x quantity squared is equal to this power series on the domain negative 1 to 1. Okay, let's do the second one. The second one is looking at the natural log of 1 minus x. Natural log of 1 minus x. Derivative of natural logs. Let's see, if I take the derivative of the natural log of 1 minus x, that's going to be 1 over 1 minus x, and then times negative 1, doing my chain rule. Okay. So natural log of 1 minus x is the integral of negative 1 over 1 minus x dx. Okay? So we can do our term by term integration. So we'll do our term by term integration and say 1 over 1 minus x is equal to x to the n, the series x to the n, geometric series. And this is valid on this domain. Remember, when you write that a series is equal to a function, you must include the domain. Okay? So I'm going to use my term by term integration to say that the integral of 1 over 1 minus x dx is going to be the integral of the sum here. And that will be the sum of the integral to be x to the n plus 1 over n plus 1. And when we integrate, we keep the same. This will be valid. We keep the same starting starting index should be valid on negative 1 to 1. So the natural log of 1 minus x is going to be the sum of minus 1 over n plus 1, x to the n plus 1. And this is going to be valid on negative 1 to 1. And then the last problem here is, well, what about natural log of 1 plus x? And there's a relationship between natural log of 1 minus x and natural log of 1 plus x, because we can rewrite this as natural log of 1 minus negative x. So since x is in between negative 1 and 1, if and only if negative x is in between negative 1 and 1, we can use the same power series representation or we can use the power series representation of natural log of 1 plus x of 1 minus x to get that of natural log of 1 plus x. Okay, so natural log of 1 plus x is going to be all we have to do is replace x with negative x. So I will have negative 1 times negative 1 to the n plus 1, x to the n plus 1. But watch this. I can combine this negative 1 with this negative 1 to the n plus 1. And I can make that simply negative 1 to the n plus 2. And negative 1 to the n plus 2 is the same as just negative 1 to the n. Okay? This will be valid on negative 1, 1. Okay. All right. So that is it for this section. That's it for our discussion of integration and differentiation of power series. As usual, let me know if you have any questions. Thank you.